So this is another vacuum chamber where we do evaporation of materials. Both of these are classes of deposition: physical vapor deposition. Sputter deposition is a cold deposition, no heating required, even though there's collateral heating. This is a hot deposition where material is heated and we rely on the vapor pressure of the material to cause deposition. So here we are using pellets, there's no cathode, there is no target. We are using a pellet and heating up those pellets. So this is a copper. So there's a copper pellet, or actually melted copper, inside a graphite crucible. Why graphite? Well, it'll sustain very high temperatures and it doesn't evaporate. Or we can use tungsten, that's more expensive. So if there's a need, like contamination between graphite and the material is a concern, we can use tungsten. But tungsten is very easy to deposit by the cold sputter deposition. You don't have to heat anything, and the sputter yield of tungsten is fairly reasonable. It's not unusually low. So we can sputter the tungsten. So which method you use for materials really depends on which is easier. And now there are differences. The sputter deposition is done at millitorr levels. It'll coat sidewalls a little bit. Whereas in evaporation, there's no gases. It's a vacuum. So it's in microtorrs. So when an atom leaves from the source, it'll just go in a perfectly straight line, which means the sidewalls and features sidewalls will not be coated. Only the top surface will be coated. So here we have, so you can see there's a filament, looks like a light bulb. It's a tungsten wire-wound filament. You put current through it on the order of 20 or 30 amps to light that up and produce free electron in the vacuum. So there'll be a cloud of free electrons, just like in a light bulb. But then we need to drive the electrons away from the filament. So we drive the entire filament up to 10,000 volts. So the electrons will be spraying out of here. And then there are magnets here on both sides that creates a magnetic field that goes left to right or right to left. And that'll bend the electron beam and put it inside this pocket. This is where the crucible is. And then this substrate sits up here. That's where the substrate, upside down. There's a shutter. The shutter just opens and closes to start the deposition. This one here monitors the deposition rate. And the deposition rate monitoring, that's based on a quartz crystal. And you measure the acoustic frequency that's oscillating inside the quartz crystal. That acoustic frequency is modified by the deposition. So as the crystal gets heavier, the resonant frequency drops, and you can measure that resonance frequency, and that's what this is doing. This is the ion gun. That's the filament for the ion gun, and it's bleeding oxygen through it, so it ionizes oxygen, and it accelerates the oxygen ions up towards the substrate, which is here. And there's the shutter in the middle. And the quartz crystal monitor is that guy there. And that's in the path of the ion beam. And that's why when we turn on the ion beam, you'll get some noise. I started this pump last night. It's down at 2 microtorrs. And I loaded titanium in the pocket. And the titanium, they're little pellets. That's already loaded. TiO2 is set. Thickness, let's just do 500 angstroms and a rate of 2.5 angstroms per second. Okay, so it looks like that's good. And this is the ion gun control. I'm just going to turn it on and I'll start it. Okay. All right, so there's the filament lighting up, 20 amps flowing through the filament to generate electrons. And once there's a stable supply of electrons, the high voltage comes on. So there it is. That's 7,500 volts, 5 milliamps. So here I can look inside. It's probably going to be too bright. All right, now you can actually see. You can actually see. That's pretty good. The bright light is the filament.
The little dot on the top, which is not in focus for some reason, is the titanium pellet. And so we can go and retrieve this TiO2. So this is an upside down configuration. That's the only way you can do evaporation. Sputter, you can do it in any direction. You can sputter down or sputter up. So there it is. These are the slides. Now TiO2 is a dielectric, so it should be transparent, and it is. But you can see that the color is not just like glass. There's a tint to it. So we can also measure the refractive index of TiO2. You can clearly see the film. You can see that little separation where there was no film where the clip was.
So if you look here,
yeah, you can see that line where the clip was blocking the